This is continuing on motion along the line, but this time we'll be discussing what happens when you have a given graph instead of just given a function. Sometimes you could be working with just a graph of velocity. So your setup should look something like this, where you have the particle's velocities given on the time interval from 0 to 16. You should tape or maybe use a glue stick to put these in your notes. Now I'm going to be using a bigger graph to kind of refer to certain aspects of it, but this graph is the same as this bigger one that I have over here. So for part A, in what direction is the particle traveling at t is equal to 2? So back to the definitions that we did, the direction is based on the sign of velocity, whether it's positive or negative. So you have to look at 2 and figure out if we have a positive velocity or negative velocity. That's going to indicate what direction it's traveling. So at 2, the graph is underneath the x-axis or underneath the axis, so it's going to be a negative. So it's going to be traveling to the left because it has a negative velocity, and that's my answer. So at 2, velocity is negative, so we can say it's less than 0. So the particle is traveling to the left. And that's the answer. That's it. Part B. For what values of t is the particle at rest? And again, going back to the definitions, a particle is at rest whenever the velocity is equal to 0. And that means graphically, something is at 0 whenever it's crossing or whenever it's hitting the x-axis. So it's 0 at 3, at 5, over at 10, and then also at 15. So velocity is equal to 0 at 3, 5, 10, and 15. So we can say that v of t equal to 0, that's when the particle is at rest. We can say that's going to be at t is equal to 3, 5, 10, and 15. So those are the 4 instances where the particle is at rest briefly before it starts moving back and forth again. Alright, moving on to part C. Find the time interval on which the particle is traveling to the right, and we have to explain our reasoning. Traveling to the right is back from the definitions whenever the velocity is positive. So we have to look and analyze this graph to see on what intervals it's positive, it's above the x-axis. Looks like from 3 to 5, the graph is above the x-axis. So that's going to be the time when the particle is traveling to the right. Also from 10 to 15, this graph is above the x-axis, making it positive. So from 10 to 15 is another time interval. So it's going back to answering this. So whenever the time is in between 3 and 5, right, that was the first interval. And whenever the time was between 10 and 15, above the x-axis, particle, we can say the particle, is traveling to the right. And then explaining our reasoning, we can say because on those intervals, we can say that on those intervals, velocity is positive. We can say v of t is greater than 0. That indicates that the velocity is positive. And that's our answer. Part D, and E is the last one, so you should hopefully be able to fit all this on at least a page front and back. Part D is A of 7 positive or negative. So now we have to kind of go back to the definitions initially as far as the equations, and we're being asked about A of 7. So we're saying that A of 7, but then we have to relate acceleration back to velocity. So the relationship between acceleration and velocity is that the derivative of velocity is acceleration. So I can say that acceleration and the velocity derivative, so v prime of 7, are equivalent based on this definition. And since I have the velocity graph, I need to analyze the derivative of this velocity at 7. And then derivatives graphically are measuring the slope, the tangent line slope. So through 7, this tangent line, it's obviously going to be negative because this is decreasing. So this has a tangent line slope which is negative. So this is going to be negative. And that's our answer. So the acceleration is negative because the derivative of velocity is also negative. Part E is figuring out if the particle is speeding up at t is equal to 9. And the last connection we have, speeding up is required by velocity and acceleration having the same signs. So we have to check the signs of velocity and acceleration at 9. So first thing I can do is say velocity at 9, and we'll look at the graph for that. And then acceleration at 9. And sort of like we did in part D, we have to relate acceleration back to what's given to us. So what's given to us is velocity. So the relationship again for velocity is that it's the derivative of velocity's acceleration at 9. Right? So graphically, the velocity at 9, it's underneath the x-axis. So this is going to be a negative velocity. And then the acceleration again is the derivative, so I have to measure the slope of this graph through 9. And just like before, the tangent slope, I just kind of lined up my pen or my marker here, and the tangent slope would be positive at 9. So it's going to be a positive value. And since these two are not the same, the signs are not the same, the particle would actually be slowing down. So to answer this initially, you would say the particle is not speeding up. And to justify, you would say that since velocity and acceleration have a different signs, since v of 9 and a of 9 have different signs. And that's the answer. And that's it for this video.